Deep Fission comes about because we made the important realization that when you're down a borehole, which we were looking at for deep isolation, you already have excellent containment. And you also have 160 atmospheres of pressure from the water that's above you in the borehole itself. So quite remarkably, you have the exact conditions that you need with cement, and you use cement and steel and above ground. And 70 to 80% of the cost of above ground pressurized water reactors is in creating that pressure and then the containment of it. So basically, we're taking 70 to 80% of the cost out of pressurized water reactors by putting the nuclear reactor a mile underground.
Just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country,
of course, the world cannot meet it without America.
that is willing to
We're going to need you, the next generation, to finish the
overhaul
job.
nuclear regulation
We need scientists to design new
and
fuels.
focus on net public
We
benefit
need engineers to invent new technologies. We
over absurd levels of radiation
need
protection,
entrepreneurs to sell those
then
technologies.
we will march towards this.
We need workers to operate assembly lines that hum with high-tech, zero-carbon
We have
components.
unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
All right, welcome back to another episode of the Fire to Fission podcast, where we talk about energy-dense fuels and how they can better human lives. Today, I'm joined by repeat guest, Liz Muller, CEO and co-founder of Deep Fission. Liz, last time we chatted, you were CEO and co-founder of Deep Isolation, and now Deep Fission. You just changed one of the words in the company name, but I'm very excited to chat about it and hear how you've been. So,
Thank you, Mark. I'm happy to be here. Happy to talk to you about one or both companies. Still involved in both of them.
Yeah. But before we dive into, I guess, kind of transition and thoughts about both, what for the audience's perspective, why don't you give us a quick background on Deep Fission, or 30-second intro pitch? What are you guys trying to do?
Deep Fission comes about because we made the important realization that when you're down a borehole, which we were looking at for deep isolation, you already have excellent containment. And you also have 160 atmospheres of pressure from the water that's above you in the borehole itself. So quite remarkably, you have the exact conditions that you need with cement, and you use cement and steel and above ground. And 70 to 80% of the cost of above ground pressurized water reactors is in creating that pressure and then the containment of it. So basically, we're taking 70 to 80% of the cost out of pressurized water reactors by putting the nuclear reactor a mile underground.
Cool. Novel concept. I'm stoked to dive into that and chat more. So before we do, when we left off last time, you were working on deep isolation. Talk to us a little bit about kind of the progress that deep isolation had made, and then, this transition to Deep Fission.
Yeah. Deep isolation is doing really well. So deep isolation is still engaging with customers around the world around deep borehole disposal for nuclear waste, how this can be done, where this can be done, how much it's going to cost, what are the regulatory hurdles that need to be overcome. So deep isolation is now it's still in some ways a startup company. We haven't actually disposed of any waste yet. But is 8 years old and has revenue, is able to sustain itself, is doing really well. And so I was able to hand deep isolation off to the chief operating officer, the former chief operating officer, who is now the new CEO. This is Rod Baltzer, who's been in the nuclear industry for 30 plus years, very experienced, had been a previous CEO before. And so he's got it. And it's both exciting and humbling to feel like I'm no longer needed in the company. I am still involved. I'm still on the board and taking on the role of exec chair. But my full time these days is with the new company Deep Fission.
That was going to be my question. Are you still involved? And it's like every leader's dream to, work themselves out of a job, like train the people behind you or under you to do your job, and then you can move on and do something else. So
it is and it isn't, because we had such a strong team, and the team of people at Deep Isolation I genuinely love and care about, and they're so much fun to work with. So as much as it is a dream to work yourself out of a job, it's also still hard to give up when you care about something. And I also think I had visions of myself still being the CEO, and the company actually did first disposal and became $1 billion company and all of these things. But I still get to be involved. I'm just going to be involved as exec chair rather than as CEO.
Yeah. Well, that's exciting. I can't wait to see the day that happens, right? I mean, it's from an engineering perspective, as an engineer, I'm like,
yeah,
there is absolutely no reason that we can't physically, mechanically do this.
Yeah.
So I commend you and the current team to keep going, and they'll get there, right? So
yes, absolutely. Yeah.
Okay. So Deep Fission, how, I mean, obviously you guys have been thinking about like boreholes, thinking about the subsurface, right? From oil and gas, we do this all the time. There's a whole catalog of tools that you can use to do stuff in the subsurface. But how did you guys get the idea or the thought process to be like, you know what?
Yeah.
We could like do a reactor in the subsurface too.
Yeah.
Why not that? Like, but
Yeah.
walk me through kind of the process that got you there.
Yeah. So we co-founded Deep Isolation because nuclear waste disposal was a significant barrier to the future of nuclear power, particularly 8 years ago. I think these days it's perhaps less of a barrier. But 8 years ago, when we founded the company, everyone was saying no new nuclear power until the nuclear waste problem is solved. And so solving the nuclear waste problem just felt like a really big, important breakthrough, where if we could succeed with that, it would unlock the entire industry. Now, over the past 8 years, a lot of that is still true, but there's also the cost issue, which I think has been encroaching on my mind, as even if we solve the nuclear waste disposal problem, it's not clear that we're going to solve the cost issue for nuclear power. And so that's been creeping up on me for a long time. And you've probably seen the reports around why nuclear is so expensive. And as I mentioned, it's largely the construction, it's the concrete and the steel, and the time frame also to build the nuclear power plant takes a long time. So I've been aware of nuclear waste as an issue, now also aware of the cost of nuclear power as an issue. And then we were asked specifically, among all of the things that could possibly go wrong when you're putting nuclear waste for disposal inside a borehole, one of the scenarios that we needed to look at was, what if accidentally, instead of putting spent fuel in the borehole, you put fresh fuel in the borehole? Is there any chance that this would start a chain reaction? And we did the calculation, and the answer was no. But along the way, there were a couple of really interesting things that bubbled to the surface. So we're very familiar with the containment that you have deep underground. That's why deep isolation, nuclear waste disposal, and deep boreholes is such a great solution. But you also have 160 atmospheres of pressure just by virtue of being a mile underground with the water on top of you in the borehole. And that started getting the gears turning, because that meant that we now have the exact same situation that you're trying to create. And the reason that you have so much construction for a pressurized water reactor is in order to create those two things above ground. And so the calculation came out, no, one single spent fuel assembly or fresh fuel assembly in a borehole a mile underground cannot go critical. But then the next question became, well, can we make it go critical? Can we come up with a design for a nuclear reactor a mile underground that would be sustainable and that could take advantage of the fact that we don't now have these massive construction costs? And that's what led directly to Deep Fission.
Awesome. How far along are you guys in this process?
Deep Fission is still relatively new. We're a bit over a year old, but we only came out of stealth mode a couple of months ago. And this is because we really wanted to do our own internal due diligence. It seems crazy when you think about putting a nuclear reactor a mile underground and that would decrease costs. I mean, if anything, it seems like you put it underground, you're going to increase the costs. And so we wanted to do our own level of due diligence to satisfy ourselves that this idea is real and that it will work, and to do a certain level of cost calculation before we came out into the public realm. So where we are now, we do have a conceptual design which has been written up and submitted to the regulator. We had a public hearing on that document. And we are now moving into preliminary design and then hopefully into final design. So we have a lot of engineering work that is happening now, going from basically convincing ourselves that this is going to work to actually designing something that is going to work, is still a very significant effort. And we're also signing up customers and continuing the engagement with the regulator.
Awesome. So talk to us a little bit about that, I guess, preliminary design. I guess I just pulled it up. So you've got this Deep Fission conceptual design review of deep borehole pressurized water reactor that had been submitted to the NRC. So walk us through a little bit of this.
Yeah, I mean, the core concept is that we want to use what's readily available without creating a brand new supply chain. So we are looking at relatively standardized pressurized water reactor fuel assemblies. So 4 of them, which would go into a matrix or a 2x2 array into a borehole. So put it into a reactor vessel, which could be thin-walled because the pressure inside the reactor is the same as the pressure outside of the reactor, or is similar to the pressure outside of the reactor because, again, of the water in the borehole. That would generate heat that would then go into a steam generator, so a secondary loop of water that would generate the steam. The steam would flash to the surface, or would shoot to the surface where you have a turbine, and you would generate electricity.
Okay. I've got a lot of questions, and if it gets too technical, then
Sure.
just stop me. We can move on. Right. So this steam and all of this is happening subsurface, right?
Yes. Well, the steam generation would happen subsurface, but then it would shoot to the surface for the steam generator. Okay. Sorry, for the turbines.
Right. And the steam generation, is it the same borehole then or same wellbore that your steam fluid flow is going through, right?
Yes. So we're looking at a single 30-inch diameter borehole for one reactor.
Okay. That's going to be my other question. Yeah, the diameter of borehole. How much space do you guys actually have to work with here? So, 30 inches is big, right? That's a big diameter hole.
Let me elaborate on that a little bit, because 30 inches is a large diameter hole, and it is also within the realm of what existing drilling companies are, I'll say, mostly comfortable with, right? So not everybody has drilled a hole to that depth of that size, but some people have. And we expect to be able to do it with available equipment today. So nothing brand new is going to be required. We may have to move some rigs around, go for a big rig, obviously, but we think that's doable. We are also thinking about a 40-inch hole. So a 40-inch hole is harder. That's potentially moves into the realm of needing to design some new equipment. We haven't fully established that yet. But 40 inches would allow us to have a 3x3 array of fuel, which would be for much more efficient use of the nuclear fuel. So there's some significant advantages to that, and we are considering both options.
Would there be any possibility you guys would go smaller, or is kind of the neutronics just not feasible? I mean, you said 2x2 array for the 30-inch.
Yeah, we could potentially go smaller, particularly if we wanted to use a more highly enriched uranium. But again, we're trying to start with off-the-shelf what is available today. And I know you've probably been following some of the concerns around the HALEU supply chain. And so we prefer to start with low enriched uranium just at 5%.
Got it. And what kind of, I guess, issues or problems are you guys protecting against? I know you'd mentioned it a couple times, like having extra atmospheres and having a containment vessel, but what's the hazard? Walk us through that again.
Yeah. I mean, there are absolutely safety advantages of going deep underground. It's hard to imagine a scenario where this would impact the surface, life at the surface. We can talk that through that. But I think the biggest advantage, nuclear reactors today are extremely safe. And so touting the safety advantages feels less important to me. I mean, yes, you can argue that it's much safer when it's a mile underground, but I think the biggest difference and what makes this so exciting isn't the safety advantages, it's the cost advantages. And it's the fact that we can be profitable from the first implementation of this reactor design. And I think that, personal concern of mine is, well, what does nth of a kind mean? How long is it going to take you to get to nth of a kind? And how much money are you going to lose until you can get there? And so having a reactor design that is profitable on the first of the kind implementation just feels like a massive win. And I think is one of the reasons that our customers are so excited about what we're doing.
Awesome. Okay, so the cost should be less. What do you guys estimate for CapEx for one of these systems? And you can give it in any metric, or even say, well, we don't know. We haven't built one yet. Like,
I will start by we don't know. We haven't built one. But I will add that you can do some back of the envelope estimates, and I would invite you or any of our listeners to do those same back of the envelope estimates, and it will probably get numbers that are not that far from our own numbers. So the biggest CapEx cost is drilling the hole. So you can get really good numbers, and we've gotten these from multiple vendors on what is the cost of drilling a hole to these specifications. We're looking at about $6 million for a single hole, and the cost will go down if you're doing a fleet of them. So if you're doing 10 holes, if you're doing 100 holes, the cost is going to go down pretty significantly. The biggest cost in our levelized cost of electricity is the fuel. So the fuel is, as I mentioned earlier, especially with a smaller design, we're not as fuel efficient as some of the other larger reactor designs. So we're trading off between fuel efficiency and not needing construction. And so with only 4 fuel assemblies, we are going to go through those fuel assemblies about every 2.25 years for a 15 megawatt reactor. So that's a lot of refueling. And we can talk about that as well. We're hoping to leave the spent fuel underground in the borehole and never bring it up to the surface again, which is pretty cool. But we know the cost of fuel today. We don't know the cost of fuel in the future, but you can also do your own calculations. What do you think the cost of fuel in the future is going to be? And those are the 2 biggest components by far of our LCOE, as well as our overnight capital. So if we're wrong and the reactor vessel ends up costing twice as much or even 10 times as much as we expect it to, we've done sensitivity analysis. It's not going to matter that much. Our biggest costs are really the fuel and the borehole itself.
Okay, so borehole $6 million, fuel, but fuel might be even more expensive, and I can go back and make my estimate for what a 2x2 array assembly might be. But, yeah. If it's more than $6 million, then that's still, say, an order of magnitude lower than what other SMR vendors might be at, right? That's kind of the thought process there.
That's right. Yep.
So, I mean, say you spend $20 million on your fuel for your 15 megawatts, right? You could still find applications that, okay, $26-30 million for your total installed. Well, and that's just my back of the envelope calculations of, man, if I could get a 15 megawatt reactor for like $30 million, I guess it depends on how many years you've got. But so yeah. That's the concept then, like have
that's the concept.
I guess single fuel assembly and then kind of your whole, call it balance of plant. I mean, you leave your power generation on the surface in a little building that you bring your steam supply into, and then you've got equipment that you presumably remove that's above your fuel assembly, and then can drop additional fuel assembly.
That's right. Yep.
What's your timeline? I know it's, again, radically uncertain. You guys submitted your regulatory engagement plan, and I think it was March that it showed up, and then quote unquote came out of stealth mode recently. But what's your current guess for when you might have the first one of these?
So we are looking to submit our license application. So we're looking to confirm our first site within, I'm going to call it the next 6 months or so, and then move forward with our license application with the goal of submitting it in the fall of 2026. We are currently assuming a 2-year review process. We would love it if it could happen faster than that, but we're aware that this is not something that you can really rush. So we're looking at hopefully getting the license approved in the fall of 2028. And then building a reactor is going to be the fastest part of it. So drilling a hole is about 3 weeks. And then assembling the various different parts of the reactor and lowering it down to the reactor, again, sort of weeks to months. So probably 3 to 6 months in order to get everything done. So commercial reactor in 2029.
Cool. And you guys are looking for the best first spot to do this.
We are, yeah. And we do expect our first customer to be with multiple reactors, so multiple holes, probably a dozen or maybe even more.
How far apart would you space these?
So based on rock analysis that we've done with deep isolation, we think 15 feet apart is plenty. You really want to look at your precision for drilling to make sure that you don't deviate from what you're expecting to drill. But the precision these days is very good. And so we could have a whole array of 100 boreholes on about an acre.
Man, it's quite precise. Yeah, you'll need very precise tools. I've drilled wells in the past, and I would give a little bit more safety tolerance than that. You could have, but you could do 15 feet on the surface and then spaced further apart in the subsurface. Just having your array of uncertainty as you drill down. Okay, that's interesting. I guess so. 2029, but the first customer might be more than one borehole. Fascinating. Circling back, so like this idea of the heat exchanger in the subsurface. I mean, do you guys have like a temperature estimate that you'll be generating steam at and then sending it back to the subsurface or back to the surface?
Yeah, so we're looking at using similar temperatures to pressurized water reactors above ground, so about 300 C. So it could be a range of 275 to 315 or so. But because of the pressure, 160 atmospheres, that be boiling until we reduce the pressure and then allow it to flash disk.
And then, like, is this, you've got one tube coming down that's pumping fresh water and the other tube that's sending steam back to surface? Like, what's that flow look like?
Yeah, so there will be a couple of different mechanisms. We will have water coming back down a tube, and we will have steam going up a tube. We will also have a sampling tube that we can use to test the primary circuit. So we can inject boron. We can test for any changes that are unexpected. There's also going to be the mechanisms for lifting things and retrieving anything that we put at depth. I touched on this earlier, but we do expect that the entire reactor vessel will not come back up again with a lifetime of just 2.25 years. We are less concerned about corrosion than you would typically be. And the plan is after 2.25 years, we would lower it down deeper into the borehole for storage. And then, of course, there's also the casing water itself, which can be used as part of an emergency core cooling system, just in case you need it.
Do you think you would ever need that? I mean, like,
no, but you want to have one anyway, right?
Okay.
You may not expect to ever use it, but it's nice to have something.
Yeah, I mean, like talk about the world's best natural convection, right? Like, okay,
Yeah,
so you've got a hot rock in the bottom of a tube. Like, okay, the water around it gets hot and then it flows up, and then you have
that's right.
thousands of feet of additional water that will circulate, right? That's kind of the whole
That's right.
concept.
Yep.
Have you guys made estimates for like the duration or lifetime of these systems? I mean, 2.25 years for one fuel bundle, but fuel bundles are what, 16, 17 feet long,
Yeah,
and you're a mile deep, so maybe you've got 1,000 feet to work with, so that's 100 or whatever, or 1,500 feet to work with, so you got 100 refueling cycles. Am I thinking about that correctly?
so if we're looking
Not
at
specifics,
fueling,
but like, hey, we'll use up part of the wellbore, um and just
yeah,
keep stacking.
we could actually drill the hole deeper than a full mile. So we could drill, let's call it, 1.25 miles, and then have the fuel assemblies at the very bottom, and so that you're able to easily maintain the pressure at a mile depth. Um, we are we are thinking about what that means in terms of ability to bring it back up to the surface. So we can bring it back up to the surface if we need to. But as you mentioned, 2.25 years, less concern about corrosion. It's really the casing of the borehole itself that is the limiting factor in terms of the lifetime of the hole. We're currently estimating 30 to 40 years. Again, it's full of fresh water. We can put material in there if we need to. Doesn't have a lot of the same materials that you would have in an oil and gas well that are potentially corrosive.
I mean,
Worst case
on the exterior
scenario.
of the casing, yes. On the interior, and because you don't have flow
That's right.
through the
That's right.
casing, your
That's right.
corrosion issues will be
Yeah.
reduced.
And because the capex is relatively low, if we wanted to say we're going to close it up after 30 or 40 years, even though we think we probably could go longer and just drill a new well, it's not going to change the cost very significantly.
Sorry, I'll say that back. So extending the life of a single well bore won't change the cost. Like the majority of the capex is
I mean,
upfront.
assuming that,
Yeah.
30 to 40 years should be pretty straightforward.
Well, and
Extending it
all
from,
financial calculations go to zero after that amount of time anyway, right?
right. So
Oh, and the
extending it to
people
60
with the money
years
that you're
versus,
solving problems for, right, are like, what? We don't care after that point. I'm retired
yeah.
and hanging out. Um, okay, what have you guys thought about? And this might be a problem that you solved with deep isolation, but what happens if you drop one of these assemblies?
Yeah. So we have done some of that with deep isolation, but you can imagine you're dropping it into a water environment, so it's not going to go crashing to the bottom. It could potentially be damaged by hitting the bottom, and you may have to, worst case scenario, abandon the well and start over.
Easy, right? It's
Yeah.
already in the subsurface. So,
Yeah.
how big's the team?
So we're growing. We were at about 15 people a couple of weeks ago, and I think we've hired a couple more since then. We're mainly focused on engineering hires right now. I mentioned we have a lot of engineering work that needs to happen over the next 2 years, so that is probably our single biggest focus.
Gotcha. Do you guys have partners in the oil and gas industry that you're working with?
We do. We've been talking to a number of different people. We're also able to draw on some of the experience of deep isolation, working with oil and gas industry. There's also the Deep Borehole Demonstration Center, which has done some of the testing that is helpful to us. But yes, we're also developing our own relationships with people in the oil and gas sector.
You guys expect to be able to control reactivity, I assume, like in the subsurface, right? So like you'll have a control rod of some sort that is able to go in and out of your fuel assembly.
And also be able to use boron as well with the tube that goes to the.
Okay. So how many? So let's see, 2x2 array. I think I've got that question answered. What are some of the biggest like hurdles or obstacles that you see bringing this to a market to commercialize it?
Yeah, I don't want to underestimate the engineering challenge ahead of us. So, it's great to have a conceptual design that you feel really good about. but taking a conceptual design to a real final design that you can actually build is a lot of work and a lot of detail. And of course, in the nuclear sector, you have to have a very granular level of design before you can submit your license application. So that is probably our biggest challenge right now. At the same time, we're also continuing to engage with the regulator. So by the time we submit our license application fall of 2026, we want every single big issue that we might have with the regulator to have already been discussed as part of our pre-application process. So going into this with a mindset, no surprises for anybody. We all want to know what we're doing as early as possible so that we can have those conversations and do any additional work that may be required.
Why did you pick a mile? I guess, was that arbitrary, or could you go shallower?
So you want to get the 160 atmospheres of pressure from the water that's above you in the borehole. And so it would be challenging to go shallower. We could certainly go deeper. So deeper is almost easier than shallower, because just by virtue of the column of water, that would create 160 atmospheres of pressure at about a mile depth.
And why the 160 atmospheres of pressure?
Again, just to keep it straightforward and the same as what you have for a pressurized water reactor above ground. So in order to generate high quality steam, you want about 160. You could also use more if you want hotter steam, which could be beneficial. So I could imagine in future designs, maybe we want to go deeper and have a hotter steam coming out. But we're starting with wanting to leverage what's already been done. This is a pressurized water reactor. It's not new technology. It's just taking existing technology into a new environment. And we're hoping that should simplify things with the regulators.
Awesome. So lots of engineering horsepower. You're leveraging the work with deep isolation. You've got a plan for coming to market, like timeline, entertaining prospective customers. You guys are doing it. It's pretty exciting.
Yeah.
What's but you mentioned you mentioned that the fuel supply and the fuel would be one of the most expensive things. So what are your thoughts on the fuel supply chain?
Yeah, it's an interesting question. I'm excited about the investments that the U.S. and others are making in an independent uranium supply chain. I think that's important. I think it's needed. I also think that there's going to be a lag, right? So, I guess fortunate, unfortunate, I don't know. We're not going to be able to use fuel until 2029. So that gives us a number of years to hopefully have this supply chain come online. We're not going to we're not going to want to use Russian fuel as we have been in the past. And so my hope would be by 2029, this is not a significant risk. Now, uranium is not that expensive to mine, so the cost I do think will come down eventually. The question is really about how quickly can we get the supply online, and we probably are going to see a bit of a price hike over the next couple of years, I would think at least, depending on demand, not just in the U.S., but also internationally. So I think we are going to see a bit of a hike, and then I would expect it to come back down. And I would also expect the long-term forecast to be not that different from what it has been historically, just because uranium is plentiful and good techniques are coming a long way in terms of getting uranium from seawater. And it shouldn't be that expensive for the long term.
Have you guys engaged with any of the conversion, enrichment, or fabrication vendors to understand kind of their timeline for the supply?
We have. We've been talking to them. Yes.
So no concerns there for bottlenecks?
I would say not yet. I think we'll have to continue to have those conversations, but I think we feel pretty good about our, again, because we're using low enriched uranium, I think it's going to be much easier to get than if we were to need Halo.
Awesome, Liz. I normally ask how can people help, but I suspect part of our audience is from the oil and gas industry. And so, yeah, if there's folks that have ideas or are curious, or they're like, hey, we
Yeah.
design subsurface tools. Like, should they reach out to you?
Yeah. Absolutely. I would say, particularly if there's anyone out there who has experience with a 40-inch borehole a mile deep, I would love to hear from them. But even just with, ideas of how that would work, or, anything that people think would be helpful, absolutely, please reach out.
What else can people do?
So I guess one of the concepts that I've been hearing a little bit about recently is this idea that the US should just hit 2 technologies and go with those. And I think that's a mistake. I think if we were to pick 2 technologies or 3 technologies or even 4 technologies, we would probably be picking ones that have been around for a while and maybe that aren't taking advantage of some of the recent innovations. Certainly, our concept is brand new, and yet because of the lower cost, I think we're going to catch up quickly. I'd just say that, let's not in our minds turn towards the concept of just pick the 2 biggest companies and expect to go with those. Let's keep an open mind, and I think the market really deserves to have a significant say.
I love that. Liz, we might have to cut this episode short because I've got to run, but leave us with your most positive vision of the future. What's it look like?
I think the future of nuclear is going to be very exciting. We are going to have low-cost nuclear power, which is going to enable us to finally address climate change while also growing our economies, having AI and data centers. I think nuclear really enables us to do it all.
I love it. We'll have to have you back on sometime in 2025 to get a progress update.
Absolutely.
And hear how things are going. And man, I think it's a really fun idea. I would say, like, a lot of people I've heard some pushback in the industry that's been like, really? They're going to put in a wellbore? And I'm like, as somebody who has put many things in wellbores, it's unbelievable the ingenuity and what people can do from an engineering and technology perspective inside a tube. So I'm excited to see you guys progress.
Yeah, thank you.